It wasn't as good as expected. It wasn't very bad. It was okay. I think somewhere 68, 70 or something like that, the averages. Now, a couple of things that I'm going to point out, and then we're going to continue with those equivalent resistances. Now, the common mistakes, I actually mentioned that before the test too, but first question, with the first question. When you're writing your expression for the power delivered, you have things like that, Vz of t, Xt, and there is no Xt anywhere on the circuit. In such cases, you will see a node undefined next to this, and I took 2 points, but second exam I'll take 1 point on that, okay? Because when this is undefined, it means that this equation is completely wrong, okay? So that's one thing that was very common. Please do not do that in the second exam. Make sure that any voltages, any variables, any currents that you are using in our equation, like you want to say power absorbed by A, for instance, equal something something, question 2. You can't write A is equal to 2.6 volts multiplied by 3.9 amps, something like that. A is not a variable. That's mathematically not a correct equation. Okay? So pay attention to how you put your work. That's the first thing. That's where you lost most of your points. Okay? Make sure that everything is well defined, any variables that you are using in your equations. Whenever you are using power or energy, we talk about that at the beginning, but you always have to have two-part subscript. Otherwise, when you say P is equal to Vz times Izt, there is no way I can tell if this equation is correct or not. I don't know if you are pointing to power absorbed or delivered, then I can't tell if that equation is correct or not. Okay? So make sure that you do not have any errors in terms of undefined variables or notation. Okay? So this is that was one big problem. Another thing, when you are the units, there was a lot of mistakes with the units. Okay? Pay attention to units. Those Vx of t and Vz of t, when you write the expressions, and some of the time you left it as y is equal to something, but what is y? Please be very specific what you are pointing, what you are defining when you write an equation. What is that? Is it the voltage, x, Vx, or Vz? Okay? Another thing, at the end of each page, right corner, please let us know where the verb follows. Okay? You will see that we had to do regrading in some papers because we read in order, and then 3 pages later there was the continuation of question 1. And we didn't see that, so we have to go back and regrade that part and all that. And at some point, actually, we had the pages mixed up too because you haven't put them all in order. So the best way to do that, at the end of each page over here in the corner, either say next page or number the pages, say go to page 6, go to page 7, so that we will know after we grade this page where to go. Okay? Now we are returning those exams back to you, so if there's anything that we missed, you can always give it back to us. But in the final exam, we will grade them and we won't return them back to you. So you will hardly see your final exam. If you want to come back and then see, but nobody generally wants to see their exam, or nobody wants to see anything about circuits once they are done. So most of the time, it's only 10% or so comes back and then see their exams. So within those pages, if there's something ungraded that we missed, that's gone forever. Okay? We won't realize that we missed that page. So the best way is for us to make sure that we grade all of your work, you have to kind of like guide us through your pages where to go next. Okay? Clear? So that's, if you do not let us know, if we can figure out mixed up with the work, we're going to take off points on that second exam. Okay? Now, the first question, second question, they are migrating. If you have any questions with the first 2 of them in terms of grading, come to me. If you have any questions for the third problem is the one that's grading. So if you have any questions, please go see Dr. Wasik. Her office number number and office hours should be on the syllabus. Okay? So everybody's gonna just look into their own grading, and so you have to go back to that instructor if you have any questions about that. Okay? If you feel like there's something mistake, or if you feel like you don't understand, you need more explanation on the grading, go see one of us. Okay? What else? What I was gonna point out on those things. Okay, so power delivered to means power absorbed by, but it was mostly in terms of the definitions. Like if you are writing something, you are writing an integral equation, you want to put dt, right? And then you are writing something like this, VZT, that's -4 millivolts per second, T plus 9 millivolts. Now, this S at the denominator is not crucial maybe, okay? Because I told you that you do not have to necessarily use the units in the intermediate equations. But this milli is essential. Milli is a number 10 to the -3, right? So you cannot just write -4t plus 9. At least this is in millivolts. You have to put this at least, even if you are not doing it that way. Okay? Any questions? The exam. So that's going to be pretty much the same case once we have your exam this Saturday. So we divide all of the exams from both sections into 2 parts. I take one part, the other section instructor takes the other part, and then we switch during the weekend and then do the other halves, and then by the second weekend we enter the grades. The following Monday we give them back. That's going to be the case for the second exam, okay? And for the second exam, homework 3 and 4, that's what you're returning, right, before the test. So it's going to be homework 3 and 4 material. Not happy with the test date, but unfortunately we couldn't get around because the other weekend is the beginning of spring break. So we are having it a little bit early. Otherwise, I would like the equivalent resistive problems, one of them in the test, but you won't have that, okay? Second exam, that's going to be all in exam 3. So exam 2 material you are looking into mainly, not, of course, it's, what is it called? It covers from the beginning.
Cumulative.
Cumulative, right? Okay. So it goes all the way from whatever we did up until now, not now, but until the resistors, series parallel combination. But emphasis is on the KVL, KCL, solving simultaneous set of equations. Those type of problems, okay? That's your emphasis for exam number 2. And, well, can you do, if you feel comfortable, series parallel combination, can you use it in the test? Yeah, of course you can use it. But we are not gonna ask you find the equivalent resistance or that kind of problems in the second test. Any questions? Okay, so then the handouts, please. We're gonna continue with those problems. Now, let's finalize this question, the first question first. I'm not drawing that, so hopefully you'll finalize it, and I'm gonna show you the final step. That's how we ended up for the overall thing. R3, R5, 9 and 10. We came up to that point?
We went further than that.
Now, remember we had a resistor that was over here, right? That was kind of like making a loop around the same noise, coming back. Now, as a general rule, when we have a resistance, there is a circuit here, some kind of a circuit, and then there is this resistor, right? Rs. If you have a resistor like that, floating, no current through it, then that's going to be irrelevant to the solution. We're going to ignore those resistors. If you have a resistor that is in parallel with a wire, that resistor is shorted, and it means that the voltage across this resistor is 0, which means current through it is also 0, right? For a resistor, I times R is V, right? So anytime current or voltage becomes 0, the other one also becomes 0, right? So in those cases, we're going to be ignoring those resistors. You can, in a given question, you can simply say that that's open circuit or that's short circuit, and then you can just cross it out. We will know that you're ignoring that resistor because it's shorted or because it's open circuit. Okay? Now, for that resistor that we had over here, we had actually kind of like 3 resistors in series to each other, which makes it like a single resistor like that, right? Now, if you look over here, in this case, which one is that? Like, situation is Rx or Ry?
RY.
That's like Ry, right? It's like Ry that's in parallel with a wire. It's this resistor in parallel with a wire. That's why that's gone. That's irrelevant to our solution, dummy resistor, and doesn't have anything to do with the solution. That's why we ignored that. That's where we stopped, I think. Okay? But could you see that? Those bunch of resistors. So, what is this handout? Have? Okay. And there we go. Let me look at that first question and video too. So, over here, if you look over to the rightmost, so this bunch of resistors that we ignored over here, they were consisted of what? Are 11, 12, 13, 14, 15, 5 resistors, right? So those 5 resistors were irrelevant to the solution. Could we see that at the very beginning just by looking at this problem? Yes, how? There's a wire completely bypassing those resistors, right? So if you look at over here, so all of those resistors, those are in parallel with this wire. Now, how could I know that that whole thing would be gone? Well, if you had a source in that circuitry over here, like a voltage source or a current source, you cannot do that. But if it is pure resistors, which is the case over here, you know that any resistive circuit can be taken down to a single equivalent resistor. Okay? So I know that, I don't care what it is, but this whole thing, from this node to this node, could be taken into an equivalent resistor, right? And this equivalent resistor would be what? In parallel with this wire here. And then what? That's going to be shorted. Do I care about this value? If it is R1 in parallel with R12, then it doesn't matter. All it matters, that's purely resistive, which will come down to a single equivalent resistor, which will be in parallel with a wire. So it's going to be irrelevant to the solution. Another way of proving that to you, last time what I did, I numbered each of those wires, right? And I showed you that eventually when you put them all together, this whole thing turns into an equivalent resistance that is in parallel with a wire, or you can think about it as a resistance that's floating. But in any case, it's just going to be a resistance that's a dummy resistance, which is not going to be affecting the solution. which means that you can ignore all 5 resistors. Okay? It doesn't matter. You can just go along the way like we did last time, and then eventually see that that whole 5 resistors turn into a resistor, either floating or shorted, and then at that point could be ignored. Or you can look at the problem at the very beginning, and you could say that, well, this whole thing is in parallel with a wire, so I'm just ignoring this whole thing at the very beginning, and then just in step 1, you can get rid of that. Is that clear? Okay? It doesn't matter that if you know that a single resistor, okay, in parallel with a wire is a dummy resistor, you know that those 2 resistors are also dummy, right? Because added together will be a single resistor in parallel with that wire. Now you can add another parallel resistor, then another resistor. Doesn't really matter. All of those can be all combined into a single resistor in parallel with a wire, which means that they're going to be just, they could be just all ignored. Okay? As long as you don't have any interest in this circle here, right? If you have a current over here that I'm interested in, then everything will be different. Okay? So the purpose is to reduce this circuit by combining series and parallel combinations as much as possible, so that I can reduce and reduce and reduce until I do not have any other simplifications to make. So in this case, that's where I stopped, I think. So now I can do extra thing here, right? What can I do? Any parallel combinations at that point? Not a parallel combination, but R6 and this resistor are in series combination, right? And then once I combine those 2, they're going to be in parallel with this whole thing. So
that's where we stopped at.
That's where we stopped. Okay, so this whole thing in parallel with, look what I'm going to do. You can't do that on the okay? So R6 and parenthesis error. Here like that, right? You are not adding 6 and 3. Be very careful with the parentheses and when you are doing those calculations. So R6 in series with this whole parallel combination, which is in parallel with that resistor here. Okay? Now to that whole thing, I can also add R7 in series, and then that's it. Anything else? Let's call this R big. A good name, isn't it? So we have anything else? Any other simplifications on this circuit? Anything in parallel?
Well, you can't combine them.
What about R1?
R big and
R1?
R1. Are they in parallel? They're in parallel, right? They have the share. They share the same note pair, same notes. Can I combine? I shouldn't. Why? IX is the current through R1, not the current through the parallel combination of R1 and R big, right? If I combine the 2, IX is gone forever. And then the circuit cannot be solved forever because of that. Then we're going to be able to find this value, right? So I stop at that point. Okay? I stop at that point, but that's okay. That's good enough to solve for everything. What were we looking for? Power absorbed or delivered for this? Delivered? So here is my current, IS. Okay? All I want is IS. After this point, how can I finalize this problem? Let's do it in a couple of steps. So does it make to write a KVL equation here? Yes, no?
You can find IX.
I can find IX, but I mean, is KVL gonna help me at all in that circuit? KVL. No, why? 1, 2, 3, 4. There are 4 components, right? Do I know the voltage across each one of them? Yes, no? Yes, what is it? 10 volts, right? All 4 components are parallel to
10 volts.
each other, which means that they share the same exact voltage. So the voltage from this node to this node is 10 volt. It's 10 volts here, 10 volts here, 10 volts here. I know the voltages for each and every component here. So KVL doesn't really make sense here. So I'm going to look into a KCL equation, and there's only one meaningful node, right? KCL at this node and KCL at this node will give me the same equation. So if you write the KCL, what do I have? Negative IS, negative IX, plus 5 IX, and I big equal 0. Looks like I have 3 unknowns, 1 equation, but I didn't use Ohm's law yet, right? Because I'm done with KVL, done with KCL, I don't have anything else left. It's only Ohm's law. Now, do I know the value of IX? Yes, right? What is the value of IX?
It's KVL and that loop, and then the voltage just is R times IX.
Exactly. Well, KVL or Ohm's law, right? Because I know the voltage across R1. If I know the voltage, I can always find the current. So 10 volts, I have, this is 10 volts, so which makes this equal to 10 volts, right? So then what can I say for the current? There's negative, right? Active sign convention. 10 volts over R1. So I know that current. Well, same way. Do I know I big?
No.
We just have to get the equivalent resistance.
Well, do I know this voltage?
Yeah.
It's again 10 volts, right? Same deal here. So I big is also equal to 10 volts over, this time in passive sign convention, over R big. And well, I don't have it here, but we know the values of R1 and R big, right? That's already given, and that we calculated. Assume that. Okay? So I got IX. If I know IX, I know this current, I know I big, put them all in this KCL equation, you get IS. Once you get IS, power delivered by the 10 volt source is 10 volts times IS. Okay? So that finalizes this, and don't have the value. That's it. Any questions? What? Any questions? Yes.
So do we add the values R3, R5, R9?
So actually those are given in the problem, right? Normally at each step, when you go from one circuit to the new redrawing, you're going to keep calculating. Let's say in that one, you have R3, R5, R9, R10 all separate, right? You redraw, and then you got R3 in parallel with R5, R9, R10. Then at that point, just next to your circuit, you should write down R3 parallel R5 equal, let's say, 5.38 ohms. And your drawing, instead of this, you should put 5.38 ohms. That's how you should show your work, okay? And so in that case, it's not going to get that messy. Every time you're going to keep calculating your resistors while you are reducing it. But please write down your calculation, okay? Because what happens most of the time, this value turns out to be wrong, okay, that is calculated. And then in order to get partial credit on that, if I know that that's this, but it's just a math error, you lose less points. But if it is only going from this circuit to this circuit, that's 538 over here and nothing else given. I'm not gonna know if this is due to a math error or you put resistors in wrong combination. Okay? Any questions? Then go back to third question, please. You are doing this on your own. We're gonna work on that, but I really want you to do that from the beginning. Now, one thing, one detail. Now, read the question first. It has parts A and B, right? Now, it's the same circuit. Could you please explain to me why you're going to get different answers for part A and for part B? Different terminals, how does it matter? It's the same circuit. Now, what does it mean exactly finding this equivalent resistance? So you have this circuit. Let's say you have different terminals, okay? Okay? Now, what do I mean when I say what is the equivalent resistance seen between terminals B and E? What is the assumption that is not shown on the question? What?
I guess they're like in the middle, so they're like the most important component. So like in the last problem we did, we gave you like the last one, like the last resistance.
The resistance seen, right? But so when we say what is the resistance seen between terminals B and E, okay? Yes.
It means that all of them can be put into some combination of series and parallel circuits, all those resistors in between them.
But the eye, right? The eye is very important. The eye is looking at the circuit from terminals what? B and E, right? Now what is the assumption here? I'm assuming that I'm looking at the circuit from B and E. So the assumption is there is something connected here that's looking at the circuit between those two terminals. That's an important detail because you're going to have, as in that problem, you have resistors here, right? Floating resistors. Now, if you are looking at the circuit from those terminals, those nodes are connected to something. So you cannot really ignore those resistors. They are not floating. Because the assumption with a resistance seen by something, this is that something looking at that circuit in between the terminals B and E. Does it make sense? Or no? So that's why if you're looking at the circuit between terminals B and E, and then there is a resistor floating at terminal D, you can say that this resistance is not connected anywhere, so it's floating, so it's this, right? You can ignore. But if there's a resistor over here connected to terminal E, right? And this is your E, let's say, floating over here, but you're looking at the circuit between terminals B and E, then you cannot really ignore this resistor. Because the assumption is you have something connected to terminals B and E that's looking at the circuit problem. Okay? So based on that, please take a look at that problem while I draw it. We're gonna assign. Yeah. start.
You can get rid of the right? This one right here, when you put it all together, does it end up becoming the same?
Is it? You have to think about it carefully. So when a resistor is shorted out, right? You have to be careful. You can't ignore everything, okay? If you are sure that you're ending up with an equivalent resistance in parallel with a wire, which is gonna short that resistance, you can get rid of it, but that's not gonna always be the case, okay? We'll talk about it.
Okay.
How do you first start on that?
Identify the nodes.
First thing is the nodes, right? Labeling the nodes. Now, when you are labeling the nodes, you have to be careful that you do not give the same two nodes, right? The same two names to the same node, right? So, if you look over here, well, the nodes are already labeled. Are they all right? Whoever did that has no idea about the concept of the node, right? So, okay, now, which names I want to stick with? Look at that. The question is asking F to J, right? And then A to L. So I want to keep those names and then correct the rest. Okay? Purple didn't look. Okay. Now let's start with J. Okay? Now I'm following this node. Still the same wire, right? Still the same wire. Now, is this H? That's not H, right? That's still J. Let's get rid of that. Following the wire. K? Again, that's not K. That's J. Still following the wire. And I think there's another name over here, right?
Yeah,
There was a C, which you will get rid of, right? That's still J. So we define our node J, okay? Now, L is good, right? It's only connecting R7 and R8, single node over here. So it is, I'm gonna leave it as it is. Now, let's look at this node over here. A is good, L is good, J is good. Let's work on F. Now, what is F? Only extended here, 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 and here. There's no other extra node labeling, right? So F is good. There's one more node over here. So let's keep E. Let's see how much this node extends. So this is the same node, right? Is it D? D is gone. That's still E. What else? There is this wire here, short, so that's going to be the same node still, right? So is this G? This not. This is still E. And it looks like we took care of all the nodes, right? That's your first step. Once you get this first step done, you're ready to do your first drawing to find out what resistors are in parallel, okay? So let's do that now. Now, when you are doing this, it's important which two terminals you are interested in. So let's get part A first, okay? And then we're going to look at part B. Or you can actually, so what we're going to try to do for part A, remember when you connect two resistors that are in series, the middle node is lost, right? When we are trying to find the equivalent resistance from F to J, we will pay attention not to lose one of those nodes, F and J. We can lose all the others, okay? But what I want to do, so that we're not going to be redrawing that twice, I want to do a first drawing where I'm going to keep F, J, A, and L, all four of them. And then when I'm working on part B, I'm going to start from this circuit instead of restarting all over again. Okay? So my interest is in keeping F, J, A, L. I'm trying to reduce this circuit to a point where I have only F, J, A, and L left. Now let's look at the circuit. this resistor is gone forever. Right? I don't have any interest in that R11. So this resistor together with B is gone at the very beginning of the problem. Now, this resistance could be ignored in part A, right?
Mhm.
But cannot be ignored in part B, because in part B, I'm looking at the circuit from A to L. Okay? So I'm going to do a first drawing where I'm keeping F, J, A, and L, and then I'm going to take care of those other parts. I'm going to start looking at A and B individually. Okay? So let's keep A now. And I'm going to use my codes for the resistors, the numbers I want to do. So this is node E, okay? Now, let's get parallel things done. So I got this already, right? E to J. What do I have from E to J? E to J. R1
R1 and R2.
in parallel with
R2.
R2. R1 in parallel with R2.
And R6.
What else? E to J, also R6, right?
And R9.
E to J, R9. Okay?
We don't have to do like parentheses for R1 and R2 when they're.
No, because all four of them. So
Okay.
what do I normally in the quiz in the exam? On the homework? How you are going to deal with that? On the side, what you're going to write R1 in parallel with R2 in parallel with R6 in parallel with R9 is equal to 1 over. Can you tell me the numbers from 1 to 69? Resistor value.
1.7 kilo ohms,
1.7.
2.2, 4.3, and 6.8.
6 point.
8.
So you're going to calculate this value, right? Whatever comes out, that's what you are putting over here in the exam. Okay? But it's just easier to explain on the board with those resistors. That's why I'm sticking with those. E to J. So now, I took care of A, E, J. Now from E to F, okay? E to F. So I'm putting a note over here. What do I have from E to F? There is R3, E to F. What else?
R5.
R5. Looks like that's it. Is that?
Yeah.
F to J. F to J. Now, J is here, right? It doesn't really have to be beautiful looking. You can make it like that, okay? F to J, or you know that you can play around with the wires however you want. Extend this J a little bit here and make F to J like this. Okay? It doesn't matter. So F to J, what we have is R4. I took R4 to here. What is left? So E to L, L to J. E to L, L to J. So E and J are here, right? So you want to maybe put L somewhere over here. So that this is E, this is J. E to L, I have R8. Then L to J, I have R7. Did we take care of everything? Did we take care of everything? You see better from there. That's why I'm asking. I really don't know. Did we take care of all of the answers, right?
Yeah.
Okay. So, see, if you had, you could just get rid of this, right? And then also L. You could also combine those resistors in series at once. If you do that, you have to start this process all over in part B, okay? So, you see, I kept L and then A intentionally so that I do not have to restart in part B. Okay? That's my common circuit. Now I'm going to start A and B separately. Okay? So, let's look at now A, part A. Okay? Now, part A, all of my interest is in F and J. I really don't care about any of the other nodes. I can lose them. Okay? So, based on that information now, what can I do here? Combine which one? You can combine R7 and R8, which loses L. Do I care? I don't. You can do that. What about R10? R10 is a dummy resistor in this case, right? Because I don't have anything connected to A. So get rid of R10, combine those two. Now we end up with R7 plus R8. This is node E. Every time you have to keep track of your nodes. So this is J. This is 1, 2, 6, 9. This is 3 in parallel with 5. And this is R4. This is F. Okay? Now, I have 3 nodes left, right? And I want to keep J and F. That's what I want. That's my second drawing. Now I'm going to go one more step. What do I have here? Those 2 resistors in parallel, right? They share the same node pairs. So this resistor is in parallel with this. Let me give this a name. R pi 1. Okay? So that what I have is R pi 1 in parallel with parenthesis 7 plus 8. And this is from E to J. And then I have R3 in parallel with R5. Then R4. Here's my F. Now what?
Those 2 are in series, the R3.
Which 2? Because at that point, those 2 are in series, right? Or those 2 in series. Or those 2 in series, right? What is important is, that's where it's very important, which 2 resistors, which 2 nodes you are looking at the circuit from, okay? Depending on what you want to keep, what you can lose, that's what's going to determine, because there's only one single series combination that is correct here, right? Remember series combinations loses a node, and you're only allowed to lose this node here. So this resistor and this resistor are in series combination, right? And then combined together, that's going to give you 2 resistors in parallel between F and J. So I'm going to do that all in one step. So if you are comfortable, you can actually combine a couple of steps in one redrawing. You have to redraw in any case, at least 2-3 times, okay? But if you want to do this and that in one step or not, that depends on you. I would suggest try to do it many drawings first, and then eventually along the way, you're going to have less number of redrawings, okay? So F to J, so what I have now is, I have RP1 in parallel with R7 plus R8. That is in series with R3 in parallel with R5, which is in parallel with R4. And let's see, that makes it RFJ. That's your answer, part A. Okay? It's like a puzzle, isn't it? It's fun. And we're going to look into part B. It's the same circuit. We're going to end up with a different result because we're going to look into the circuit from 2 other different terminals. Okay? And the whole reason that I did this circuit, I kept all those 4 letters here so that I'm not going to restart from this, but I'm going to restart from here. So let me try to go on the bottom, okay? For part B. What am I trying to keep now? I want L and A. I want A and L. Okay? What can I do? It's not a dummy resistor anymore, right? It's not a dummy resistor anymore. What can I do?
R3 and R5 are in series with R4.
R3 in parallel with R5 is in series with R4, right? Do you agree? And series combination, what do I lose? F. I don't care. I can lose this, right? So R8, R7, L in the middle. And then we have, okay, let's do this in a couple of combinations, okay? In one step. R3 parallel with R5 is in series with R4, which will lose F. And this series combination will be in parallel with this resistor over here, right? So let's combine them all at once. This, you can see this color thing. So R1, R2, R6, R9 is in parallel with R4 in series with R3, R5. And this node is, what is that node? This is the one on the bottom is J, right? What is this one?
E.
That's E, right? J is F is lost. So this is E. So I still have A, L, E, and J. Now,
R7 is in series with all of that.
okay, now R7 is in series with R8. R7 is also in series with this whole junk, right? Now, I don't want to combine 7 and 8 in series because then I lose L. But I'm okay to combine 7 with this because I'm going to lose J only, which is okay. So I'm going to do this series combination at the bottom, which is going to give me A, R10. So I'm taking R8 here and L here. And I'm combining those two resistors, and that's going to be from what? L to E. So this is E, and this is L, and extend it a little bit. There is no way I'm going to write this one again. Let's call this R, E to J, okay? So that's R, E to J plus R7, series combination. One more to get rid of, and then I'm done. I want A and L. I want to get rid of E, right? Correct? So let's finish this. Let's take it down to a single resistance from A to L in one step. What do I have here? I have R8 in parallel with this series combination here. And then this parallel combination is in series with R10, right? Which is going to get rid of E. So I have A to L. What do I have? R10 in series with parallel combination of 8 REJ plus R7. And that whole thing is my answer to part B, which is RAL. Okay? Okay? Any questions? Yeah.
8J, not E. But the last one where we combined everything with J and F. That one. How
Here.
come? Yeah, they're all in series. But we
Yes.
combined the J to F so we can get rid of E. But how come when we did series with that, we did parallel with R4?
Okay, so at that point, and that's A, right? So you have J and F. Everything is in series, right? What do you have to pay attention when you are doing series combination? Whenever you know that two resistors in series, that's not good enough. In order to decide if you want to combine them or not, you ask yourself, am I interested in the middle point? that between those two resistors. And those are in series, right? This resistor and that resistor. Are you interested in F?
Yeah, you would want F.
Right? You don't want to lose F. If F is gone, you are messed up for that question. Right? Because you're looking for the equivalent resistance from F to J, right? So you want to keep F, then you can't combine those two. If you combine this resistor and this resistor, do you want to do that? You have J in the middle. J will be lost. You don't want that. This resistor and this resistor are in series, right? In the middle you have E. Can you lose E? Yes, you can. That's why we combine those two. And then that's, of course, we skipped a step. Yeah, when you combine those two, you had a single resistance going from J to F, right? And that's resistor, series combination is from J to F. R4 is also from J to F, so we concluded that they're in parallel. And then we combine those two in parallel over here. R4 in parallel with this whole thing. Okay? All it matters, it's not a big deal when you're doing the parallel combinations, because parallel combinations keep the resistor, keep the nodes, right? No node is lost when you are doing when you combine two resistors in parallel. But when they're in series, then you have to be careful. That's how you get rid of each and every node one by one, and then you arrive. The goal is to arrive at that only have those two nodes left, whichever you are interested in.
So we conclude that R4 is parallel with J and F. Why do you
R4
Yeah.
is it in J and F, right?
Yeah.
When you combine those two resistors, E will be lost, and then the series combination will be in between what?
The J and
So they share the same node pairs, right?
Yeah. So
That's why they're in parallel.
Okay.
Okay? Any other questions on this? Okay, let's go back to question 2 then. Okay. So the last question is very similar to what we did here. I don't want to go through that one.